means discussion was included, and I'm really very thankful to the course coordinator for giving me a slot to discuss something about deep learning. Thank you. So let me share the screen first. So my slides are visible, Dr. Upen?
Yes, sir. Your slide is perfectly visible. And
okay, thank you. So as the name is deep learning, okay, so learning is fine, but why this deep has been attached to this learning? What is special about this deep learning? So as the title, I have given deep learning a humble introduction, so that very easily we should know what is the concept or the principles behind this buzzword, that is the deep learning. Okay, so before starting this deep learning, with the permission of the coordinator, I just want to start with a short video. So, Dr. Upen, my screen is visible?
Yes. Your screen is visible, sir.
All begins from a single origin, a unique point in space and time.
Can you hear the video's audio?
This is the spark of innovation.
Yes, sir.
Fuels your most amazing breakthroughs. It's a passion for discovery that unveiled the genesis of all that exists in the universe. Today, the power of AI helps computers achieve superhuman capabilities in image recognition, and lets scientists save our most precious resources by analyzing in 1 month what used to take 10 years.
是谁发明了机械计算机？
Everyday devices translate even the most complex languages from voice into text and images into words.
Xavier is now present.
Helping the visually impaired recognize an old friend, or letting a blind woman read to her child for the first time. Autonomous vehicles give us the freedom to reimagine our city streets and travel where there are no streets at all, to help the lost find their way home. We see robots teach themselves to perform simple tasks. We even watch in awe as they take their first steps. And today, a 2,500-year-old game meets its match as a computer competes with one of the greatest human champions of all time and wins. This is the collective imagination, fueled by forward-looking technologies and the beginning of your most amazing discoveries yet to come.
So again, jumping to this presentation. So probably you must have got some idea about the deep learning. So basically, if I say, then this deep learning is penetrating in almost every domain of science and technology. And being a little bit hypothetical and philosophical, I must say that after maybe 5 to 10 years, everything will be governed by data-driven approaches, probably the deep learning. And moreover, you can say, okay, there may be some advanced methods where the learning will be just like humans. There may be emotions involved. There may be some biases, and anything. Means whatever you can think about the humans, that can be included in the machines. So this is the future. So okay, I'm not boasting the field, but yes, obviously, this is the right time to start thinking about this domain for variety of applications, even in the domain of physics, materials, metamaterials, photonics, everywhere. So with this pretext, let us start about this concept of deep learning. So before starting the concept of this deep learning, I'm just posing few things. There is a question, how human learning is different to this deep learning or machine learning. Are both the learning same or altogether different? If these are different, then how these are different? And what are the ways to equate these two learnings so that in future the machines should behave just like humans? Okay, so in my opinion, machine learning is not different from the concept of human learning. Okay, so let me take an example and just pose something. Suppose there is a kid of only 2 to 3 years, maybe 1.5 or 1 year. He just started knowing or learning something. Then what is the way to learn by the kid? So probably all of us must have observed this thing. Okay. So suppose the kid doesn't know anything about one fruit, that is apple. Okay. So what happens? You show the apple, the kid may be inquisitive enough, knowing about the apple. What is this? Okay. So you show the apple, kid will touch, kid will perceive the appearance, everything. And then, okay, kid will be convinced and okay, will associate the word apple with this particular object, which is slightly round in shape and maybe reddish green or yellowish green, yellowish red color. Okay, so it is labeled object now in the mind of the kid. Okay. Sometimes you show some different kind of apple, means every time what happens, repeatedly you present this apple or show this apple to the kid many times. Then what happens? Then kid is quite confirmed. Now it is learned, you can say okay, whenever there is new apple, it is not the same apple which was presented long back, but still the kid will say, okay, this is apple.
Sorry to interrupt you. Sir,
Yes.
are you moving your slide or only?
No, I'm still. Okay. So this way the kid will come to know, okay, this is apple. Okay. So how these kids are knowing that this is apple before? I mean, sometimes it is not necessary to taste the apple. Okay. Simply by presenting the pictures or the object itself, kids will learn that this is apple, this is guava, this is orange, whatever it is. You present, and slowly, with time, some information will be fixed in kids' mind, and it will be tuned that this is apple, this is guava, this is banana. Okay, and consider the example where you present slightly, I mean, entirely different kind of apple, maybe the complete green apple. Okay, that is very similar to the guava sometimes. Okay, then what will be the issue? Rather than calling it as apple, the kid may say, okay, it is a guava, because this is near to the appearance of the guava. Why? Because kid has already learned the apple, but the kid is not able to generalize. Okay, kid is not able to generalize. So this is the thing. So human learning, basically we say, okay, humans are intelligent. Then what is intelligence? So intelligence involves two things. First one is the learning. Okay, learning means learning from the past experiences or the data itself. Means the data which has already been produced. Not talking about the future data or future examples. Okay, means on the basis of the past, the kids or machines will learn something. This is the learning capability. Means if the similar type of example is presented to the kid or the machine, both of them should be able to label it, okay, it is apple. But what about the examples which were never presented to the kid or the machine? In that case, another factor of the another part of the intelligence, that is the generalization capability. On the basis of variety of experiences, the machines should be able to generalize, just like humans. So for humans, there are many situations. Unknown situations are encountered by the humans, and humans are able to take the decisions. Okay, so this is the part of the generalization. So generalization as well as learning, both should be there. Then only you can say your machines are intelligent machines. So with this thing, what is learning? So improving performance through experiences. So why we hire the experienced persons? Okay, maybe altogether for different purposes, but still we want experienced persons, because the experienced persons might have seen a lot of, maybe infinite number of examples in past, and on the basis of those examples, these experienced persons may take some rational decisions for some meaningful purposes. So improving performance through experience means you keep on presenting the data and your machine should be able to perform better and better. So getting a computer to do well on a task without manually building incompetence. It means it is not required to program it. It is not required to prepare some rule-based systems, means rule-based methods. Okay, if it is happening like this, then take this, otherwise take this. Earlier in means ancient, at very early stage, AI systems were basically the rule-based systems, then model-based systems. Now the AI systems are completely different, and these are the data-driven systems and very near to the humans itself. Okay. So what is deep? Here, learning is fine, means learning via the examples or the data which has been already generated or presented. But what is deep? So learning using multi-layered neural networks. So since we are making it analogous, that neural networks are analogous to our brains, okay, that's why here we are, in plain words, this sentence has been taken, learning using multi-layered neural networks, because our brain is also a multi-layered neural network. So what are the role of these layers, basically? If it is a multi-layer, what is the role of these layers? This is important. The role of these layers is simply the hierarchical representation of the data. And that happens in deep learning architectures or machines, as well as in human brains. We will try to establish this fact. Okay, so that's why we will call these machines as deep learning or deep machines, similar to the human brains, because human brains also used to work in the similar manner. So what is the relationship between the deep learning, machine learning, and AI? AI is quite old term. Okay, it was introduced long back. So as I have already highlighted, that all the rule-based systems, okay, where you need to program something on the basis of certain rules, were coming under the AI. So various pathfinding algorithms and many things were developed using these AI techniques. And then machine learning systems came into the picture, where the domain expertise was quite important. Okay, because suppose you want to present some data, sometimes the data is very chaotic, and you cannot infer out of this data, infer anything out of this data. In that case, what is required? Domain expertise is required, and you extract some meaningful, useful, smaller data set. Means this is a derived data set from the original data set. Okay, so basically this derived data is simply known as the feature vectors. So on the basis of feature vectors, you used to take certain decisions. So this was the concept of the machine learning. So feature engineering was very much required, or very much important. Domain expertise was very much required in case of the machine learning systems. Then deep learning systems came into the picture, where the approach is completely data driven. Approach is totally data driven. The kid doesn't know anything about the fruits. Kid doesn't know anything about the this animals. It doesn't know anything about the plants or anything. Still, he is able to learn that this is elephant, this is the lion, this is apple, this is a guava, whatever it is. How? Because it has not experienced. Still, it can know, it can predict, it can classify the objects. Okay, it can learn and it can generalize as well. So this was the concept of the deep learning, where no modeling, no rule-based system, only data-driven approaches will be used. And the machines itself will try to extract the feature sets, will try to generate the feature set or the representation, and those representation will be used for the decision making. So with these things, let us discuss something about the history of this machine learning, basically deep learning. So in 1943, McLeod-Pitts, basically they have given the first neuronal model, first neuron. Okay, and we can sense the year 1943. Okay, so long back. So neural network research started long back, but somehow, initially people tried this neural network or the perceptron for solving some complex problems. They were able to solve some linear classification problems. Okay, but for a smaller system, they were able to solve some nonlinear systems as well. But when the problems were quite complex, means if you consider the huge data, okay, in that case, their model was that bulky and it was not possible to train that model. Okay, there was no method to train the model because of the bulkiness of the model as well as the huge data for complex applications. Okay, so the field was completely died out, and up to 1980, people stopped talking about the deep learning. I mean, this neural networks. Then some groups were there; they were continuously working or were doing the research, and then they came up with some groundbreaking results or methods. And then again, this field evolved. And deep learning, the field of deep learning is not very old. This concept has been coined in 2011-12 itself. Before that, there was no deep learning. So you can assume that this is a very new concept. And from here, this is historical work in 1943. And this article was published in some newspaper itself. So from here, I just want to highlight a few things. Just a minute. Cursor is not working. Anyway, so here you just read the last part of the first column. Rosenblatt, designer of the perceptron, conducted the demonstration. He said the machine would be the first device to think as the human brain. Okay, this was the prediction at that time in 1943. As do human begins, perceptron will make mistakes at first, but will grow wiser as it gains experience, he said. So this statement was very important. And in today's context, this is completely true, because humans also used to learn in the same way. First, there are certain mistakes or certain errors. These errors are being corrected, and at the end, the humans are near to perfect for certain tasks. Similarly, machines will be, and this was just an anticipation at that time. And today it is true. So in 1969, another work has been reported where the title was a sociological study of official history of the perceptron controversies. So basically here, some sociological aspects were included, okay, and that were predicted for the artificial neural networks, okay, means neural network models. It means machines are not simply machines, okay. These machines may include some sociological aspects as well. Okay, so this was really interesting study. Some people may be interested. And then in 1980, Fukushima neocognitron model came into the picture. Means neocognition concept was developed. So this was inspired by findings of Hubel and Weiss about the hierarchical organization of visual cortex in cats and monkeys. What does it mean? It is very simple. Hierarchical organization of visual cortex. What do you mean? If we talk about the hierarchical representation, means first the lowest level representation, then slightly higher level, then mid level, then slightly higher level, then the most abstract representation. Because how humans used to understand. Human used to understand means initially they frame something, it is unknowingly being extracted in the brains, and the last layer level only some, most abstractive representation is being presented for the decision making. Means human brains or any brain used to recognize in this way or used to function in this way. So that was explored, or you can say that was unexplored basically. This was hidden. So this concept was introduced by Fukushima's neocognitron model basically. Okay, means hierarchical representation or layered architecture of the brain. That's it. Means at various layers, various hierarchical representation will be done, and at the last layer, the most abstract representation will be generated, and the recognition or any decision making will be done on the basis of this most abstract representation. So in 1986, back propagation came into the picture. Means earlier it was assumed that means the models were quite bulky and the problems were quite complex with the huge data. Then it was not possible to train the model. Means suppose the machine has taken some initial random decision. Whether the decision is right or wrong, we need to calculate the error. Okay. If it is very far from the ground truth, then we need to correct the machine. Means we need to correct or fine tune the parameters of the machine. Okay. Then again the error will be calculated. But this process was quite bulky because there were almost infinite number of connections. Okay. And it was not possible to update those weights. Basically, those connections were simply known as the weights, similar to the human brains. So it was not possible. But with the introduction of this back propagation, people started training those machines. Means there was a proper method to train those machines with the help of these back propagation. In 1989 to 1998, basically, convolutional neural networks, this was the first Linet 5 model which came into the picture, where some hierarchical representation was done, and at the same time some concept of local receptive field, just similar to the human perception have been used. Although this model was very small and it was used for the digit as well as some character recognition for means some low level tasks. Means the tasks were not very complex. For example, if we need to recognize the digit, there were only 10 digits from 0 to 9. Okay, but still the concept of local receptive field was introduced, because for all practical signals, suppose there is a time varying signal and you consider a point. Okay, I'm just taking one example here, so kindly bear with me. There may be okay, there is some issue. Anyway, leave it, because I believe that there is some issue. Anyway. So, means if you consider any point in time varying signal, what happens? The point under consideration is maximally correlated with its neighborhood. Okay, with neighboring points. And as we are moving away from this center point, what happens? The correlation starts decreasing. Okay, it means almost all the practical signals are highly locally correlated. And this is exactly the concept of local receptive field. You concentrate on a point on any scene, what happens as we are moving away from this point, the correlation decreases. Okay. This is very practical and intuitive thing. So in 2012, this first AlexNet model came into the picture. This was again based on the hierarchical representation. There were variety of layers. So basically the concept of convolution process was totally based on the concept of the local receptive field. Since at that time the compute facility was not that great, that's why two parallel paths were considered, and some low-level GPUs were used to perform this learning task, complete this learning task. And those jobs were feeded in parallel. Okay, and that somehow they were able, they were able to succeed. They were succeeded in their thinking, and they could train the machine. Okay, for some slightly complex task of image recognition. Okay, or what is image? Image is basically a two-dimensional or three-dimensional or n-dimensional data. That's it. You consider this simply as data. So they were able to design or train this particular model in 2012 itself. So we can say first established model, deep learning model, was basically the AlexNet. In 2018, Hinton, LeCun, and Bengio were awarded with this ACM Turing Award. Basically, in computer science field, this is the highest acclaimed, highly recognized, or you can say the topmost award. Okay, so first time it was given to the neural network researchers. Hinton is from Canada, LeCun and Bengio, means this group was continuously working for neural network research. When the field was completely died out, it was completely washed out. After that, even after that, they kept on working in this field, and today this particular field is going to change almost every phase in every domain, whether it is biological science, medical science, it is material science, it is engineering, it is computer, everywhere. These concepts are going to be applied, and people are applying and getting the wonderful results because these machines are intuitively very near to the human brains. That's why these machines are performing the best. So this basic model, if we talk about this perceptron and other things, so perceptron, we know very well that the perceptrons were kind of neural networks, were based on the concept of neural networks, similar to the human brain, okay? But somehow these machines were able to solve only linear classification problem. Okay, linear classification problem means with the help of some plane or line, we can separate the data into two parts. That's it. But in case of non-linear problems, what happens? Suppose you're having two classes A and B, then what will happen? The data for A and B will be quite interspersed, and sometimes with the help of line or plane, you cannot separate these two classes. In that case, your decision boundaries should be non-linear in nature. And to draw those decision boundaries by using the machines is quite difficult. So how to draw the non-linear decision boundaries was the actual problem. So people started talking about the non-linear classifier, this and that, many things in typical machine learning domain. But what is this non-linear classifier basically? So all of us know, again, I'm just highlighting one thing. Suppose there is some issue, okay? There is some issue. And there are only two people who want to solve this problem, okay? So sometimes the problem is very complex, very, very complex. And two people are not able to solve the problem, then what happens? Naturally, you try to include some more people, you try to discuss with some more people, and still if the problem is unsolved or unsolvable, then you again increase the number, okay? So at the end, suppose the problem is solved, at that time, rather than having only two people, you were having 10 people in your basket. All to will discuss and try to solve, and ultimately they solve the problem. So what is this basically? What is this? Practically, this is not, this is not anything other than the projection. This is simply a projection. Means earlier there were two-dimensional data, okay? Then you increase the number of people. It means you're projecting from lower dimensional space to higher dimensional space. It means the data, means the problem was projected from lower dimensional space to higher dimensional space. Very precisely, all the machine learning models, basically in case of the deep learning models or neural network, we use to do this thing. Okay, it means we try to project the data from lower dimensional space where actually the problem was non-solvable or unsolvable with the help of the linear machines. But in case of higher dimensional space, the data will be distributed in such a way so that now linear machines can separate this data into two classes or can solve the problem. Again, in that domain or that space, we are using the same classifier or similar linear classifier, but now the problem is solvable. It means there is simply a concept of projection, projecting from lower dimensional space to higher dimensional space. It's very precisely in all neural network research, whether it is deep neural network research or simple multi-layer perceptron, whatever it is, everywhere, for every classifier, we used to adopt the same practice. And this is very intuitive and very near to the process of solving the problem by the humans. So, machine learning versus deep learning. So, most machine learning methods work well because of human design representation. It means feature engineering and input features. Got it? Machine learning becomes just optimizing weights to best make it final prediction. It means simply optimize the weights or parameters or the connections in the brain. Means you simply tune the connections in the brain just to solve some particular task. So machine learning in practice, describing your data with features a computer can understand. So there may be some numerals, some logic, etc. Not exactly logic, some numbers are there. Means from raw data, you derive some data. Means you derive some representation. Okay, and that representation can be used to take the decision. That's it. So domain is specific. Okay, knowledge is very much required in case of typical machine learning methods. And then learning algorithm may be some optimization or weight management or weight setting by some linear classifier. This was the task of this thing. And sometimes even after feature representation or feature engineering, the problem is non-linear in nature. In that case, you project this feature from lower dimensional space to higher dimensional space and then do the linear classification. But in case of the deep learning, feature engineering is not at all required. So from here, we can understand this thing. A machine learning subfield of learning representations of data. So basically, this is a subfield of learning representations of data. Exceptionally effective at learning patterns. So patterns must be there basically. What are patterns? Patterns are the basically features. But deep learning algorithms attempt to learn multiple levels of representation, means hierarchical representation by using a hierarchy of multiple layers, similar to human brains. So if you provide a system tons of information, okay, it begins to understand it and respond it in useful way. Exactly the same process is being followed by human understanding. So this is typical pipeline of machine learning. There may be some input, some feature extraction or domain knowledge is required for this. So some feature extraction will be done, and then this extracted features will be fed to the classifier, and then some decision can be taken. But in case of deep learning models, there is no requirement of feature engineering. There is a model itself will run. Model itself will learn the feature representation. Means there are many layers in this machine, and every layer will be responsible for some level of feature. Means hierarchical features will be generated. At the end, there may be some linear classifier, and that linear classifier can predict. Okay, so there is a basic difference between the machine learning model and the deep learning models. So why is deep learning useful basically? So manually designed features are often over-specified sometimes. Means if you over-specified means, suppose you need to define something. You need to define something, then sometimes you use so many representations, sometimes which are not actually required. Sometimes which are actually not required. For example, suppose you need to describe the human. So you describe the number of hands, number of legs, the width, the length, the height, everything, the color. But if you say humans are having hair in head and you describe the dog, then what will happen? Again, you will describe this way, dogs are having the hair. So how the machine will behave? What is the use of this information? Basically, this is misleading information. It was not useful. It is not useful for the categorization of those objects, humans and dogs. But it will mix. Representations will be interposed now. So this is kind of over-specified or sometimes incomplete. Okay, sometimes it is incomplete. It is required to represent that, okay, the humans are having 2 hands, but you have not mentioned, then what will happen? If you need to categorize between human and birds, there will be some problems. So this is incomplete representation. So at the same time, if you don't know about the domain, then exact features will not be extracted. This is the problem. Means sometimes over specified, sometimes incomplete representation in case of typical machine learning. So learned features are easy to adapt, fast to learn. But in case of deep learning, since it is domain specific knowledge is not required, feature extraction is not required, so you don't need to bother about the features. So easy to adapt and fast to learn. Adapt means features can be extracted itself for a particular type of application. Okay, and it is very fast to learn as well. It is otherwise what will happen? First you learn the domain and then represent with the help of the features. So that's why deep learning facilitates in this way. Deep learning provides a very flexible, almost universal, learnable framework for representing word, visual, and linguistic information. It means whether it is word, visual, or linguistic information, everything is data. There are some numbers, that's it. Can learn both unsupervised and supervised. Both way deep learning models can learn. Okay. Effective end-to-end joint system learning. It means we need to not intervene in between. We need not to know what is happening layer by layer. Okay. We are interested in the input and the decision. That's it. And utilize large amount of training data. Here, if the data is small, there is no meaning of deep learning models. Means for deep learning models, since these are very near to the human brains, large number of experiences or examples must be presented to the system. If the examples are very less, you cannot have intelligent system. So deep learning models are almost useless if the data is very less or examples are very less. But this is the era of the data. Very easily we are producing terabyte, petabyte of the data for particular application every day. Okay, so huge data is there. So that's why deep learning is possible. Learning which is near to human is possible. So in 2010, deep learning started outperforming other machine learning techniques. Okay, even in 2014-15, deep learning system just defeated the humans for particular tasks. It means in limited sense, we can say, okay, machines are better than the humans. And the future will be there. Then for almost every task, the machine may take over the humans. So deep learning is learning representation of features basically. So here, traditional model for pattern recognition means there is some you can say there is some data, handcrafted features or feature extraction will be done. Okay, and some trainable classifier can be used. But here, trainable feature extractor means feature extractor itself is trainable. And it will train itself on the basis of the data and the decision. So you present the data, feature extracted will train itself and it will extract the most appropriate feature for classifier. That's it. So architecture of mainstream pattern recognition system. So here we consider this speech recognition. So this was discussed. I mean, this pipeline was followed in early 90s to 2011, where there is some signal, MEL frequency, cepstral coefficient were extracted out of it, and then mix of Gaussian kind of unsupervised methods were used, and then classifier was used in supervised manner, and we were able to recognize this speech. And this was typical pipeline. But if we consider the object recognition, then from 2006 to 2012, this was a typical pipeline. Means there was some data, low-level features were extracted by using this shift or HOG or many. There are hundreds of these feature descriptors, and then unsupervised methods were used for the mid-level feature representation. So k-mean, sparse coding, etc. were used. Then pooling was used in some nonlinear manner just to have the nonlinearity in the system itself, and then classifier in supervised manner to take the decision. So this was typical pipeline up to 12. But in case of deep learning, learning hierarchical representation, what does it mean? It means there is some data. Initially, low-level features will be extracted or will be generated. So from here, this is visualization. So from here, you can see that there are certain lines, points, etc. are drawn. Okay, from the data itself. So these are various planes. Okay, I'm not going into the deep itself, means at layer level, but still you can understand some very low level features. For example, if you are shown some image, then you can say, okay, how many dots are there, how many lines are there, how many edges are there. Then you combine those features, and then you will come up with these kind of mid-level feature. Then you combine those features, you can come up with these more structured feature. So for a particular type of object, for example, from here you can see, okay, this is for the bird itself. This feature, this channel is for the bird. So if there is a bird, this will be more active, remaining will be less active, and on the basis of this activity, classifier will be able to predict something. Okay, it means dots, lines, edges, etc. Combination of those dots, lines, edges, and then combination of those mid-level features to higher level features. So at the end, the most abstract representation of this image will be generated, or any data will be generated, and decision will be made on the basis of that abstract representation. So abstractive representation is the key concept of the deep learning, similar to the human brains. So trainable feature hierarchy, how it can be understood. So hierarchy of representation with increasing level of abstraction. Means as we are moving down the line, more abstraction is being generated. So each stage is a kind of trainable feature transform. So image recognition, this is typical task. First is the pixel. Pixel is the some numerical value for each and every place in the scene. So pixel to edge, to texton, to motif, to part, to object. And who will decide the object? The classifier. So this way representation will be generated. So there may be elephant, there may be man, there may be kid, there may be fruit, whatever it is. According to those objects, these features will be generated in this way, and final decision will be made. Similarly, for the text, character, word group, clause, sentence, and story. And suppose you need to find out the sentiment in this story, whether it is positive sentiment or negative sentiment, then decision will be made at this level itself. Means some sort of classifier. Similarly, speech sample, spectral band, sound, phone, phoneme, word. So this way the representation will be done. Okay. So this is the beauty of the deep learning. So learning representation, a challenge for machine learning, computer vision, AI, neuroscience, cognitive science, and many other domains. So how do we learn representation of the perceptual world? This is a question, and somehow this is addressed by the deep learning. ML/AI, how do we learn feature or feature hierarchies? That is again solved by the deep learning, basically. Means these things are considered by the deep learning architectures. The neuroscience, what is the concept? How does the cortex learn perception? Okay. So deep learning architectures are based on neuroscience kind of, these kind of analogous architectures. So way of solving the problem by the deep learning architecture is similar to the human brains. Cognitive science, how does the mind learn abstract concept on top of less abstract ones? Okay, so you can understand that all those big questions means that how model can address these issues. So basically, there is a solution which is layered architecture, that is a deep learning architecture, which can cope up with these kind of issues. So deep learning addresses the problem of learning hierarchical representation with a single algorithm, or perhaps with few algorithms. So what is there? At each and every level, there is some trainable feature transform. Means training is done for each and every layer. Okay, and abstract representations are being generated. And at the end, the most abstract representation will be used to take the decisions. So I'm just trying to correlate this thing. The mammalian visual cortex is hierarchical. So now I'm just trying to correlate these deep learning machines with the brains. So the ventral recognition pathway is in the visual cortex has multiple stages. For example, retina to LGN to V1 to V2 to V4 to PIT to AIT, up to some motors. So lots of intermediate representation from input to output. How this can be represented? So I'm just reading, and all of you are requested to please pay some attention on it. And whatever I'm trying to justify, please see this thing. Monkeys can categorize complex visual stimuli very quickly with reaction times that averages 250 to 260 milliseconds, but that can be as short as 180 milliseconds as well, depending upon the task or the training itself. Okay, so information from retina is relayed by lateral geniculate nuclei of the thalamus, LGN, before reaching V1, the primary visual cortex. V1 is the primary visual cortex. From there, processing continues in areas V2 and V4 of the ventral visual pathway before reaching visual areas in the posterior and inferior temporal cortex, PIT and AIT, which contains neurons that respond specifically to certain objects. Okay, but what is different? What is new in it? The inferior temporal cortex projects to a variety of areas, including the prefrontal cortex, PFC, which contains the visually responsive neurons that categorizes objects. Okay, it means various places of this brain are responsible for various tasks, and the signal will flow through those places, means will pass through those places, since it is required to perform those tasks. So here, to reach the muscles in the mind, to reach the muscles in the hand, signals probably need to pass via the premotor cortex, PMC, and primary motor cortex, MC. Okay, means from here to spinal cord to respective limb. Okay, before reaching to the motor neurons of the spinal cord. For each processing stage, there are certain numbers, so there is a minimum and maximum time has been given. So from here, we can we can visualize the signal is passing through this. At V1, simple visual forms, edges, corner, etc. are extracted here. Okay, suppose if this portion of the brain is damaged, then this monkey may not be able to recognize, because these lowest level features are not extracted by the brain. Then V2, some slightly higher, and that V4, intermediate visual forms, feature groups, etc. are formed here, extracted. And in this AIT, high-level object descriptions, face objects, etc. are extracted. And here at PFC, categorical judgment decision-making is done. So basically, a lot of experiments were conducted on this monkey brain, and they came with this conclusion. It means information in the brain is being processed in very hierarchical manner. So if you want to design the most efficient machine, that should be very analogous to this brain. So trainable feature hierarchies I have already said this is end-to-end learning. At every stage, trainable feature transform will be applied by default and hierarchical representation will be generated. So I'm just taking some examples now. The state of the art in vision ImageNet challenge. So here this ImageNet challenge is the computer vision World Cup. It means they have created and continuously they are improving the data set, making it more complex. And every time they invite the researchers worldwide to solve this problem. And people are coming with their own algorithms, improved algorithms, and reducing the error rate. Okay, so AlexNet was the first established deep learning model, basically in 2012. The error rate was 16.4. Then Ziller and Fergus net in 2013. There was no difference between these two, but some optimization methods were described, okay, by Ziller and Fergus. So it reduced to 11.7. Then VGGNet in 14, 7.3. Then GoogleNet came into the picture in 2014 itself. Number of parameters were less in case of GoogleNet, although the GoogleNet was 22 layer, but VGGNet was only 19 layers. So both were performing almost in the same way. So two models were the winner 1, winner 2. In 15, ResNet was there. Its error rate was 3.57. Then ResNet, GoogleNet. So concept of inception. So hybrid network was proposed. So its error rate was 3.06. And then CNET 2.25. And now the accuracy, this error rate is close to 1% only. So from 2014 onwards, okay. So from 2014 onwards, for this particular task, there were millions of the images in this ImageNet data set. Millions of the images in this ImageNet data set. So humans were not able to perform that well compared to the machines. Means machines completely outperformed the humans from 2015 onwards for image recognition task by the humans. Humans means were completely failed. So after that, for image recognition task for this particular application of particular data set, most improved machines came into the picture. So this is the height. This is not completely high, but this is the height of the machine for image recognition. Basically, recognition means for recognition tasks, machines are just beating the humans. Then vision detection and segmentation. Many machines have been reported for object detection. Suppose there is a scene, then how many objects are there? What kind of objects are there? Is it possible to comprehend this image? Okay. For example, if humans need to describe, okay, we can say, oh, there are 4 people sitting together. There is a table, there are some wine glasses, etc. We can define. Now machines can also define in the same way. This is the error. Faces, image generation. I'm just taking those examples just to show means what machines can do nowadays. So there are faces, there are some original faces, but here what happens, some artificial faces has been generated which were never the part of the database. Okay, which were never the part of the database, still the faces were generated. Machines were able to generate the faces. So can you assume that what may be there in the near future? What are the threat areas? People can generate the data, illegitimate data, just to fool somebody, or just having the malicious intentions. So there is a big threat, and people started thinking about this thing, how we can cope up with these kind of attacks. Here, for image generation means big GAN means generative adversarial networks were proposed to synthesize new kind of images. So synthesize ImageNet images means conditioned on class level up to 512 by 512 resolution, means very big images can also be synthesized by the GANs. Means machines can generate, although these images were not the part of the data set, still they can generate. If still they can generate the images, machines can generate the video, machine can generate the data. Sometimes it is for the meaningful purpose. Sometimes it is for some malicious purposes. So for some cases, machines were not able to generate, but yes, people are doing fine-tuning and coming up with improved models for this particular kind of application. It means machines are learning the density data, means density distribution, and then trying to generate the same kind of distribution, means same type of density, means adapting the density and generating. So this kind of task is being done for these two-dimensional signals. It is possible for every kind of signal. For vision application, Facebook accessibility tool for the visually impaired. A lot of things are being done. AI beats human pathologists at detecting cancer, basically. So initially, computer-assisted diagnosis were started, but now deep learning models are in position to beat the human observers. But still, it is required. Why? Because just due to lack of large number of pathologists and huge time was required. Suppose you need to analyze any biopsy sample, then how much days will be required to reach up to certain decision? That depends upon the expertise of the pathologist. So is it possible to help the humans for the mankind? Yes, machines can help. Technology behind the Snapchat chat lenses, etc., means some sort of modification, means everything. Here, vision working too well for faces, but sometimes it is little controversial as well. For example, how China uses high-tech surveillance to subdue minorities. But yes, this is controversial issue, but yes, it is being followed. It means there are some camera devices where the database has been already maintained. At the back end, images, means facial images, are being captured, and immediately entire information which is basically associated with the database is being displayed. So immediately you can find out who is the person, what is the background, is there any criminal record, this and that, everything is tagged. But this is being used with the minorities there in China. Similarly, the secretive company that might in privacy as well. I mean, here, means these are some news articles basically, just to highlight something. So here, what happened? In this case, wrongfully accused by an algorithm. So you can refer those news articles. So here what happens, there were some automated facial recognition systems. These systems were used just to investigate whether the person is having some criminal record, this and that or not. Okay. So, but here machines have taken the wrong decisions and they have declared that this is having some criminal background, but actually the person was not having the criminal background. So on the basis of machines, some decisions were taken and it was declared criminal, some penalty was imposed on it, but later on it was proved wrong. So these kind of issues are all also there. Here what happened in this particular, using the concept of deep fake video, the actor was altogether different, but machines were able to replace this actor, okay, in the movie itself. So vision working too well, deep fake faces basically. So what happens here, you can replace the face of a person completely. For example, Honorable Prime Minister is speaking something about something, and then you can replace his speech with some different things. Or he can adopt the way of speaking something, means which he never spoke, which he never produced, but still that can be produced by the machines. So this is really a big threat for all of us. So from here, input is like this. Okay, the input is a man, and output is a, basically means we have extracted the way of talking, way of speaking, emotions, etc. on some female faces, basically. And ultimately, whatever being done by this male object will be seen to be done by this female object, although this female object never did that. Okay, so these kind of things are there. Similarly, in natural language processing, the deep learning is working like anything. So language translation, Google, this and that, we all of us know very well, but what is the technology behind is basically the deep learning. So I'm not going to discuss much about the natural language processing, but this is another area of application which you can explore something more. So basically in 1954, Georgetown IBM experiment was conducted. So there is some historical importance. So it was completely automatic translation of more than 60 Russian sentences into English. This was the first attempt. Only 6 grammar rules were used, 256 vocab words restricted to organic chemistry, means the domain was also fixed. Promised that machine's translation would be solved in 3 to 5 years. It means this was just an anticipation. 1966, Automatic Language Processing Advisory Committee was formed, and it has made certain statements which were looking little hypothetical at that time, but now in reality it is true. Then ELIZA was the first chatbot which was introduced in 1966, simulated a psychotherapist, could fool naive users. Basically, it was chatting, but people were thinking, okay, some humans are just responding. So these were machine learning based models. But what happens, state of the art is speech and language. It was, error rate was decreasing. Around 80-90% accuracy level was reached up to 2000. But from 2000 to 2010 or 8-9, it was almost saturated, and no progress was made in these domain because of the lack of the learning algorithm, mechanism. So back propagation and gradient descent were the jisko bolte hain Ramband for this particular domain. And after that, with the introduction of deep learning concept, again the error rate decreased, and now we are moving in the era of about 1% or less than 1% of the error rate for speech and language tasks. So several big improvements in recent years in NLP: machine translation, sentiment analysis, dialogue agent, question answering, and text classification. So leveraging different levels of representation, words and characters, syntax and semantics, means now there is era is going to come that we will talk about the emotionally intelligent machines. And this will be possible just because of the cognitive, just because of psychology, and just because of the deep learning. There will be a conglomeration of these fields, and people will be able to design these kind of emotionally intelligent machines. So neural network, this natural language processing, neural machine translations, the great AI awakening, Google Translator is one of the example. Many things have been done. Games means, if we talk about the intelligence or this thing, generalization capabilities, so games are the best examples, which are based on complete generalization capabilities, learning as well as generalization, full utilization of generalization. Until you are good generalizer, you cannot win a game. That's it. So 1955 to 59, Arthur Samuel programmed a digital computer to learn to play the checkers. This was just start. 1960, Donald Michie built a machine out of 304 matchboxes that could learn play tic-tac-toe, and then means it has moved further. In 2013, DeepMind uses deep reinforcement learning to beat humans at some Atari games. Atari game was very famous. Okay, so basically here machines were able to beat humans for Atari games. Machines beated the human. That's it. And this game was quite benchmark game, which could assess the human brain. Intelligence of human brains. So 16 DeepMind's AlphaGo system beats Go Grandmaster Lee Sedol. So basically, after this, for this, we have seen this part in the first video as well. So after this DeepMind AlphaGo system, Lee Sedol left the domain, and his career was completely finished. 2017 Alpha 0 learned to play Go and chess from scratch. It means earlier machines were trained, but here what is happening, Alpha 0 learns to play Go and chess from scratch. It means it started learning and improving itself eventually with time. It means now in 2017, systems started performing similar to humans, performing and behaving similar to humans. 19 deep minds StarCraft 2 AI is better than 99.8% of all human players. So you can imagine this thing. It means nobody has programmed these games. Basically, these games, I mean, the algorithms behind or the architectures behind these games learned itself and made themselves better than humans. So there is a big threat associated with these type of tasks. In near future, there may be machines which can beat humans in almost every domain. Similarly, for robotic applications, I'm just putting the things. So recently, robots started learning many things. Means earlier these were programmed, but now they are improving their performance by learning. Okay, and these are various embedded platforms. Sorry for this slightly messy presentation. There is some issue, that's why it is happening. So here, these platforms for simulation, AI to Thor or Habitat can be used. Real robots, Pi robots can be used. Robots on your smartphones, so open bots. All these things can be used. So you can have this assembly and you can run your algorithms on this mobile phone, and this can act as a robot. It means a lot of platforms are being developed, and after some time, robotics will be quite easy. It means almost in every house we can expect a robot. Self-driving cars are there. Means this is very big task. A lot of companies like Tesla and Nvidia itself are engaged in developing the world's best intelligent self-driving cars. So we started talking about machine ML basics. So linear classifiers are one class, then multi-layer neural networks with the help of backpropagation. It was possible eventually. Initially, neural networks or the perceptron were used only for the linear classification problem. Okay, this is a very old trend, and then it has improved because of the backpropagation. People were able to fix those weights, means learn those weights. And then convolution neural network came into the picture by utilizing the concept of local receptive field. And then network for detection means we can detect variety of objects in a scene. Similarly, we can detect anything in data, any kind of data. It may be two-dimensional data, it may be one-dimensional, or it may be n-dimensional data. Then network for dense prediction. Suppose you have the data and you want to utilize something. I mean, you want to segment it, means extract some sort of information, or regenerate or synthesize. Then these kind of networks, means encoder decoder network kind of things can be used in slightly modified. Then generative models, GANs and variational autoencoders came into the picture. These are very new concepts. So what happens, we can learn the density function and we can generate the similar density function. Okay, it means suppose in the data set you're having certain type of data, then you can replicate similar kind of data, although those data was not the part of the original data set. So sometimes it is possible. We can synthesize. For example, you're having some thermal profile of any scene. Okay, and what is the corresponding visual profile? So with the help of those machines, you can generate corresponding visual profile as it is. Okay, so this is possible. So for variety of applications, these can be used. Then recurrent neural networks are the part where sequential data analysis can be done. Suppose you're having some one-dimensional data, you want to infer out of it, you want to get some insight, then RNN models or LSTM models can be used for this. And these are recent concepts, transformer concepts have come into the picture, okay? And this has been introduced in 2019-20 itself. So now people started shifting their focus into the transformers, and people started talking, okay, these transformers are almost everything. These transformers can do almost everything out of it. So basically, the local as well as temporal information is being processed in these transformers. So both kind. Okay. And this deep reinforcement learning means quite intelligent machines are being developed by using these concepts. So you can have some hybrid kind of architectures having the concept of reinforcement learning, recurrent network, and CNNs, depending upon your applications. So very briefly, I'm just going to highlight few things. I'm having 7 minutes with me. So this is first architecture, I mean deep learning based architecture. So convolutional neural networks. So convolutional neural network, CNN, is the sequence of convolution layers. So we know, all of us know very well about the convolution and correlation. So here process of convolution is being, so convolution layers interposed with the activation function and other layers. So here what is happening? We are using some kernels just to have the convolution, okay, and feature maps are being formed after convolution. So there are 1, 2, 3, 4, 5, 6, 7. Suppose here there are 7 convolutional kernels, okay, and 7 times this image will be processed. So 7 layers will be 7, depth of 7 will be obtained here. And then pooling will be done. So pooling is the transforming from higher domain to lower domain. I mean higher dimensional space to lower dimensional space by generalizing it. So some sort of nonlinearity will be used in case of pooling. Pooling may be the max pooling, min pooling, average pooling, median pooling, whatever it is. So some sort of nonlinearity as well as generalization capability will be included at this level. Okay, and then again convolution will be done on this. So 1, 2, 3, many convolution kernel will be used on this volume of data will be generated. Then again pooling. It means hierarchical representations are being done. At the last layer, there may be some, maybe 1, 0, 2, 4 things. I mean length, and that will be fed to some linear classifier or probabilistic approach. Means any classifier may be used here. So CNNs basically utilize the concept of local connectivity, weight sharing, handle multiple input channels, and handling multiple output maps. Okay, so these are the properties. Local connectivity means concept of local receptive field. Weight sharing, just to reduce the number of parameters to be learned. So learnable parameters are quite less in case of CNNs compared to the fully connected neural networks or multi-layer neural networks, as previously done. So variety of architectures means are there for CNNs: AlexNet, VGG, GoogleNet, ResNet, DenseNet, RCNN, Fast RCNN, Faster RCNN, YOLO SSD, etc. Continuously, benchmark architectures are being designed by the researchers and being used for variety of applications just to beat the human performance. These are typical applications: classification, object recognition with face, biometrics, biomedical, image recognition, etc. Detection, object localization, face detection, pedestrian detection, human detection. Not only here, in case of, suppose you want to apply this for finding some material defect, okay, so you can use these models for detecting the material defect as well. Means you can map these these models with your applications. This is autoencoder network. So basically encoder decoder concept is being used. So here this is a latent space representation. So from very high dimensional representation to low dimensional representation means we train the encoder decoder network together and then we disconnect, and then what will happen? Suppose you have huge data, its minimized representation will be done with the help of encoder, and with the help of decoder you can reproduce. So for image compression and other things, these kind of architectures are being used even for the segmentation and feature extraction, finding some area of interest. These kind of architectures are being used. So fully convolution networks, recon nets, segnet, UNet, mask RCNN, etc. These kind of concepts will be used. These are applications: semantic segmentation, medical image segmentation, dense prediction, depth map prediction, image retrieval, image to image translation, image enhancement, and many more. Then the concept of generative adversarial network, that is the GAN Okay, so this is also very, very useful network where the concept of adversary is being used. For example, there is some point of conflict. I say yes, then some other person say no. Then again, I produce some different proposition. I say yes, the person may say no. Then again, I will correct it. I will say yes, the person may say no. So this way, just by using the concept of adversary, people solve some problem. And this was the benchmark work. Okay. So basically, this was done by Ian Goodfellow and their colleagues. They were sitting in a bar. They were discussing about some problem. In the bar itself, in the night, they could come up with this concept. Goodfellow went to their lab. He encoded, and they have developed this thing. And there is a single book on deep learning that has been written by Goodfellow. So this was just a discovery. Means problems can be solved with the help of adversary similar to the humans. The sample generation, image to image translation, text to image, face pose, face aging, image deraining, means some sort of hazing, dehazing, inpainting, super resolution. Many things have been done. Means GANs are having huge applications. Then RNNs, so basically, as we know very well that RNNs, whenever there is a requirement to analyze some sequential data or temporal data, in that case, recurrent neural networks can be used. So many advanced RNNs like LSTM and GRUs have been proposed. Are there? You can use these networks directly to predict something. Suppose you're having one-dimensional sequential data or temporal data. You can use those networks to predict something. So sentiment classification, RNNs can be used. So goal was to classify a text sequence such that a restaurant, movie, or product review, tweet, etc. as having positive or negative sentiment. You can use RNNs. Text generation, you can use image captioning. You can use machine translation. You can use stock market prediction. You can use material property prediction. You can use, okay, many things. So variety of deep architectures are possible. So there is a feed forward, feedback, means just flow of information, or bidirectional machines like deep Boltzmann machine, where some concept of graph and probabilistic approach will be used. In case of deep Boltzmann machine, stacked autoencoded, etc. So 3 types of training protocols are possible with the deep learning models: purely supervised, unsupervised, layer-wise, plus supervised classifier on top, or unsupervised layer-wise plus global supervised fine-tuning. Means all those concepts are available with the, not concepts, flexibilities are available with the deep learning models. So I'm just skipping those concepts. And there is a question, which models are deep basically? 2-layer network, 3-layer, or n-layer network is deep. Okay, so basically the concept of projection must be done. The concept of local receptive field must be done, and the concept of weight sharing must be done. Then only you can say that your model is deep model. Means any general model cannot be considered as a deep model. I'm just skipping these concepts basically. But yes, if you have interest, then you should include those things. And with this thing, I just want to close the discussion with a question. The question is simple. When we were having the neural network, then what was the need of deep models? Okay, so means how deep? How deep? Okay, so it's very simple to answer. If we are making the model deeper and deeper, it means these kind of weights are increasing, number of weights are increasing. What is weights? Weights are treated as the memory element. So as the memory element increases, the brain's capacity is basically increased. So there is intuition. Suppose you're having huge data, infinite amount of data, then your model must be deepest just to include, just to get some insight out of this infinite data. If your brain is not capable enough, okay, to contain the information, problem cannot be solved. So that's why if you have huge data, and this is the era of the huge data. So that's why deeper and deeper models are required. So that is true with the human brains as well. When there is a kid, its brain's capability is less. As time passes, brain's capability means all the weights are basically updated, and that's why it is known as quite matured or quite experienced person, similar to the deep learning based machines. तो आपके पास अगर बहुत ज्यादा डेटा हो तो आपको बहुत सारी लेयर्स लेनी पड़ेंगी. लेयर्स जैसे ही लेंगे तो वेट्स बढ़ सकते हैं. तो वेट्स बढ़ेंगे तो उसके लिए वेट शेयरिंग कॉन्सेप्ट आपको यूज करना होगा. ठीक है. वेट शेयरिंग मैकेनिज्म से नंबर ऑफ पैरामीटर्स विल बी रिड्यूस, बट स्टिल learnable, I mean, there will be huge number of connections. With this thing, I'm just closing the discussion. Okay. And I'm just requesting all of you, this topic may not be really related to you. Okay. But yes, consider my request that after 5 to 10 years, you'll find that the entire domain of yourself will be filled with these kind of algorithms. I just want to share one paper. I mean, you just read this paper. This has been published in Nature, basically. I don't know much about this thing, but 132,000 access has been done for this paper. So recent advances and applications of machine learning in solid state material science, basically. So here, they are convinced about these deep learning architectures. They talk about this typical machine learning pipeline. Okay. And this has been published in Nature itself. I mean, this is a very reputed journal. So you can find some sort of insight, some sort of application, how these things can be mapped with the abstract concept of DL, means concept of material science with the concept of deep learning. Okay. So you can find out. Please read this paper, classification issues, and we have already seen these kind of decisions, whether to analyze the stability, and this is typical CNN model they are talking about. This is auto encoder decoder, as we have already discussed. They talk about and they are using. These are adversarial, generative adversarial network GAN models they are talking about. We have seen this thing. So this may be a good motivation to start the work in this particular domain. Okay. So this is all about the deep learning and its application. And after, I mean, earlier we were talking about this, the fact that computers are pervasive. Means everywhere, every field, it will cover everything. Then we talked about internet is pervasive. We talked about mobiles are pervasive. Now we are talking that deep learning will be pervasive in nature, and this will be treated as a basic skill set for each scientist, engineer, not only those persons, but the school kids as well. Thank you very much.
Thank you so much.
Thank you, Satish sir. Thanks a lot. So now the questions are welcome from the participants, if you have. So even though I was looking on internet, so there is just recent one Nature paper in Nature Photonics on the title of Deep Learning for the Design of Photonic Structures.
Yes.
Just I was looking, it is in Nature. So it is really very interesting. I will also share with you the DOI of this paper, so that if you are interested, you can go to the paper and see. So basically now all the research scientists have a lot of data on their material science studies, and if you are going to apply this data in deep learning techniques, you will give new insight to those data, because whatever we have studied is a very small part of the inference we have taken from the data.
Yes.
But because we have a lot of possibilities to collect the data, to store the data on our machines, so on just saving and storing the data, we have to find out the insight from the data which we have not seen. So this lecture will help you, and I have requested especially to Professor Satish, please give us a little knowledge about the deep learning, because we are hearing about the deep learning, but we have no information what is deep learning. So as a physicist, as a scientist in other fields, if our participants will go through these documents and these information, I think it will help them in future. And I again thank you, Professor Satish sir. He has given his valuable time to discuss these subjects with all of us. So if you have a question, please write to the discussion box also, or you may just ask Satish sir is here, or
Sure.
if later on if you want, you can just mail us. I think he will be happy to answer those questions if any query anyone have. So Upenji, do you like to have?
So actually, sir, I have two questions. Hierarchical representation, sir. I want to know about the hierarchical representation. If any images that can be deep learner machine that can understand by the machine. So firstly, their hierarchical representation will be generated using some programming or using some.
No. Here, in case of deep learning, no programming is used. Basically, what happens, we have used certain algorithm just to update the weights. What are weights? Weights are the memory elements, basically. So the machine will learn itself what should be the weight. Eventually, slowly it will learn, and it will update the weights to generate the best features at variety of levels, various levels. Maybe low level, lowest level feature, mid level, or highest level. So programming is not required. Means no rule-based programming. Rule-based systems will be employed in case of deep learning models.
And based on that thing, we are creating some artificial images.
Yes. Artificial. Now, I am showing the images because visually it is easy to understand, but it may be any kind of data because it is generating the same density from the same sample space.
Okay.
Basically, image is a kind of example for the data. Because data may be any kind of data it may be.
Yes.
So I think in case of a deep learning, what I understood, the input is data and output is data. And from that we have to get the information.
Output is any decision,
any decision, any information.
Yes.
Yeah.
It may be classification, it may be regression, it may be segmentation, it may be anything.
Yeah.
Thank you, sir. Yes, if any of you have any question, then you can write to us. We will try to address these things. So probably you must be having the questions in material science and other domain, but yes, you can think of considering this domain as well.
Yeah, it is a new kind of thinking. Means the way we are thinking about the material science and data is a different one. But what sir has suggested, it is a kind of way of thinking. There is a new way which can be thought of, and the data will be helpful for that purpose also. So let's thank Professor Satish sir again, and his very.
Thank you so much, sir.
So thank you, sir. Thank you very much.
Sir, I have a doubt.
Yes.
Sir,
Yes,
actually,
please.
the deep learning structures required a huge amount of data. Do we get that much amount of data in this area, that material? Actually, I'm very new to this material science area. I was familiar to image processing, but to know this latest trends, that I have joined to these sessions and all this. So what my question is that in the material sciences area, do we have that much amount of data?
No. Actually, there are certain processes. For example, there is a concept of domain adaptation. What happens? Suppose some model, that's why at very beginning it was said that these models are kind of universal models. So suppose CNN architecture has been trained on ImageNet dataset. Then what happens? In your domain, you're having certain similar kind of data, but very less data. Then you can use the concept of transfer learning just to fine tune that model, okay, on top of the earlier trained data set. It means it is not necessary. Means you can adapt that domain. You can use it for your own application. It means training is not required from the scratch. Okay, you simply find application. Means with the small amount of data, it is possible to fine tune the network. So in India, still a lot of institutes and universities are not having huge compute facility. But people started producing huge paper. I mean, large number of papers in this domain. How it is possible? Because these people are using the fine-tuned models, means some sort of fine-tuning techniques, and they are coming up with new applications and new ideas.
Sir, is to generate this data augmentation techniques also be used?
Data augmentation, basically, yes, data augmentation is being used because if you want more generalization, then your model must be trained with more noisy data, kind of thing, you can say. So more augmentation is required just to have more and more generalization capability. So these are some processes which are used in training the deep learning models. Yes, data augmentation is used, but the purpose of data augmentation is not to increase the data. Purpose of data augmentation is to include or enhance the generalization capability of the model itself. Means to work just like humans. Humans are having great generalization capability.
Yes, sir. Thank you, sir.
Thank you.
So let's thank again Professor Satish sir
Thank you,
for
sir.
his nice talk.
With
Thank you,
your
sir.
permission, I will take your leave. Namaskar, and namaskar all the participants.
Thank you, sir. Thank you.
Thank you.
थैंक यू सर
So उपेंद्र जी नेक्स्ट टॉक कितने बजे है 45 5 मिनट
11:45.
ठीक है तो हम बस 5 मिनट वेट कर लेते हैं सर अनंता सर आते होंगे सो ही विल ज्वाइन
ओके ओके.
प्रोफेसर अनंता सर का है ना इसके बाद
हाँ, अनंत सर का है.
ठीक है ठीक है Good morning, sir.
Namaskar.
Good morning,
Yeah.
sir.
How are you, sir?
I'm all right. Thank you. Thank you so much for asking me to join you. And I'm very happy to be with you.
Thank you, sir. Thank you. And so, shall we start?
Yeah, I'm ready.
Okay. So, Upen, please continue.
So, I welcome to sir in the second day of this 5 days ATAL program on fundamentals and applications of photonic crystals and metamaterials. And now let's welcome our second speaker, Professor S. Anantha Ramakrishnan. Currently, he serves as director in CSIO Chandigarh. Before joining CSIO, he served the Department of Physics IIT Kanpur. He earned his doctorate from RRI Bangalore and worked on the theoretical aspects of light propagation in random media, including temporal signatures of Anderson localization. He pursued his postdoctoral research from Imperial College, London, under the supervision of very renowned physicist Sir John Pendry. He worked in the area of metamaterials and plasmonic nanostructures materials and published more than 115 research articles in reputed international journals and also near about 70 papers in conference proceedings. And there is a research on monograph entitled Physics and Applications of Negative Refractive Index Materials. His work on metamaterials and plasmonic have drawn enormous attention from the scientific community and have been highly cited. He has recently been focusing on the implementation of metamaterials into the real life application and work on several projects of the defense agencies on various applications. He has expertise in variety of areas such as nano and microstructuring of non-conventional materials like polymers, ceramic and metals, thin film deposition technique, and electromagnetic computer simulation development. He is an awardee of prestigious SS Bhatnagar Award that is awarded by the CSIR India. He is also a recipient of Swarna Jayanti Fellowship that is awarded by the Department of Science and Technology, India. So let's welcome our speaker, Professor S. Anantha Ramakrishnan, sir. Sir, kindly unmute yourself, sir. Unmute.
Yeah. Thank you so much, Dr. Upendra Kumar. I am thankful for your introduction. It was very generous and perhaps not needed. When I was preparing for the talk today, let me just project my slides. Are you able to see the slides?
No, sir, right now it is not.
Not yet?
Yes, now it is.
Now you're able to see it, right? Okay, thank you. So I made a small correction to it. You see, metamaterials are of course very general, and a single session would not be very easy to cover all aspects of metamaterials. So I decided to concentrate on anisotropic metamaterials and look at a few applications where you can use them. And this will also fit the theme of the FDP more in photonic technologies, because I will actually be focusing more on them than the radio frequencies or microwaves. So as it was remarked, I'm at CSIO Chandigarh right now, and I'm on leave from the Department of Physics IIT Kanpur. A lot of the work that I will be presenting to you, which is our own, were carried out at the IIT Kanpur. Yeah, so let me take you all through a very quick definition of metamaterials. What are metamaterials? You see, meta usually means beyond, as in metaphysics. Metamaterials means beyond normal materials. These typically imply composite materials with periodically repeating units. These units, structural units, are much smaller than the wavelength of the radiation. It could be, when I say radiation, it could be light, it could be radio frequency, microwaves, it could be optical, infrared, or it could even be sound. It could be waves of any kind. It could be sound, it could be vibrations, it could even be seismic waves like earthquakes. It could be water waves like tsunamis, whatever. You can talk about them. So for all these cases, you can actually build structured materials which have very different properties than what are actually found in natural materials. And you have to measure these properties over a scale larger than the wavelength. So you're measuring it over a scale of many, many times each structural unit. So the metamaterial properties that you get may have actually very little to do with the bulk material properties of the materials making up the structure. So one of the nicest definitions of metamaterials was actually given by Walser in 1999. He said, look, these are macroscopic composites. This is not a single material. These are multiple materials. And they have a man-made three-dimensional periodic architecture. So you have specially shaped geometric units which repeat themselves. And these units, when you put them together, you think you have a composite. And this composite, you think of the composite now, you don't think of the units anymore, has been designed to produce an optimized combination not available in nature of two or more responses to specific excitation. So right from the beginning, what you wanted was, you wanted it to be multifunctional. You wanted it to react to two or more responses, not just one. Because you go to all the trouble of making these structured materials, you better have more than what is available in nature. In fact, much more what is available in nature. So what are some unusual properties of metamaterials you get? You can have, usually the material properties you talk for electromagnetism are dielectric permittivity and magnetic permeability. And in nature, these numbers are not very different from unity, about 2, 3, you don't have numbers which are very, very different. Very rarely in some frequency bands you can. But with metamaterials, through the resonant nature, you can create them to have very large numbers, very small numbers, near zero numbers, negative numbers, and so on. And you can also create extreme anisotropy. When I say extreme anisotropy, what do I mean? See, you have all heard of nonlinear optical crystals, which are used to do, frequency doubling or tripling or wave mixing. And one thing that you resort to there is that your wave at omega and wave at 2 omega, let's say you're doing a harmonic doubling, their phase matching should happen. So that will happen in a specific direction, because the wave at 2 omega has a different refractive index, the wave at omega has different refractive index. But it so happens that the crystals you chose are very anisotropic. So at some particular orientation, the phase velocities of these two waves, the refractive indices of these two waves will match. That's what is called phase matching. You do that with a crystal. But then if you look at it carefully, those crystals have a refractive index difference for the two waves of maybe 0.1, 0.01, 0.02, 0.03, something like that. Maximum is about 0.1 in some very strange, very esoteric materials. But in these kind of metamaterials, you can create such anisotropies. In one direction, it is almost like 100. In another direction, it is 0. Dielectric permittivity, let's say you take. And in one direction, it could be positive. Another direction, it is negative. This is called indefinite tensor. And these kind of very, very extreme anisotropies become possible. So that makes metamaterials a beautiful case study for studying effects in optics and microwaves, which are not attainable in normal media at all. I mean, you simply don't have such responses. We will come to more details later. Other interesting things you can do a perfect impedance match. You're not just doing an index matching. You do an impedance match. You match both the permeability and permittivity. You can match very large, you can have very large chirality coefficients. Again, like anisotropy, when you talk of chirality is all axial It's a basically the axial components, the magnetic and electric fields are coupled. So now the glucose molecule, for example, is chiral. But if you look at the chirality coefficient, let's say they call it by number kappa, that kappa is of the order of 10 power minus 5 in glucose. Or similarly for even very, very chiral liquid crystal molecules. But then in metamaterials, you can get that kappa down to about of the order of 1. So 0.1, 1, and so on. So this is the enormous large chirality coefficients you can get, but we will not be discussing that or the bioinosotropy in this today's lecture. So there is also this concept of negative refractive index materials. So what is that concept? I'll very quickly address in this slide. So normally when you have epsilon and mu, which is the dielectric permittivity and permeability, you can plot all materials on an epsilon mu plane. Depending on the epsilon and mu, you locate it in different regions. Normally, our whole world has been confined to this top first quadrant, which is positive epsilon, positive mu. That's where the normal world of optics and microwave electromagnetics is. Then you have this quadrant where it is negative permittivity, which is like an electrical plasma or a metal conductor. There the waves decay evanescently into the medium and they don't propagate in the medium. So that is also known in nature. The fourth quadrant, which is negative magnetic permeability. So in principle, you are talking something like a magnetic plasma. You don't have true magnetic plasmas because there's no magnetic monopole. But what you can do is you can actually create structured materials which have huge magnetic dipoles which are just sloshing around. So when the huge dipoles are actually sloshing, being excited, it looks in some frequency band as if there are actually magnetic monopoles which are very far away from each other. So that is the region where it actually starts looking like a magnetic plasma. And it will screen the entire electromagnetic wave from the medium. The wave cannot propagate in the medium. And there are some natural magnetic materials up to gigahertz frequencies which provide you such mu negative. That is in a finite band only. Then finally you have this fourth quadrant where both the mu and epsilon are negative. And then you have waves which have, let's say a wave is propagating in a particular direction. What do we mean by propagation? Energy is flowing from, let's say, left to right. That is the direction of the pointing vector given by E cross H. Then what you would find is if you make both epsilon and mu negative, then if you take the Maxwell's equations here on top of the screen, what I've written, these are the Maxwell's equations for a plane wave. So when you switch the sign of mu, you get a negative sign here. And when you switch the sign for epsilon, this negative sign becomes a positive sign. So what you end up having is, you're having a plus sign here and you're having a minus sign there. When you swap the numbers here from positive to negative. So once you do that, you will find that E, K, and H now form a right-handed triad, not a left-handed triad. A left-handed triad, not a right-handed triad. So the K and S actually point in opposite directions. That's why these are called left-handed media. EHK form a left-handed triad. They are called negative refractive because the refractive index, the refraction vector points in the opposite direction as the pointing vector and so on. Now these are possible only in artificial structured composite metamaterials. In metamaterials will allow you to access all the quadrants. Now let me very quickly go through what are the kind of sizes of the metamaterials we are talking about. I'll show you some pictures so that you become very clear. When you are talking about metamaterials for radio frequencies, the size of the structure units will be about 1 centimeter. When you talk about it in microwaves, it will be of the order of a millimeter, 1, 2, 3 millimeters or smaller also slightly. Then when you're talking about almost terahertz waves, you're talking about 100 micron scale. And you're talking about few terahertz into the infrared, you're talking about 5 to 10 micrometers. And by the time you are into the LWIR, MIR, you're talking about 1 micron structures. And at optical, you're practically talking about optical and infrared frequencies, you're talking about 100 nanometer sizes. So the corresponding fabrication processes will change, and you go from normal conventional machining or normal conventional practices all the way into very, very highly sophisticated methods of nano and micro fabrication. So as an example, let's look at the first metamaterial that was designed in the world. These are just metal wires. So what you do is when you put metal wires here and there in vacuum, these metal wires give an incident wave, the idea that there is some conductivity there. But then the electrons are not present everywhere. They are only present in the wires, and they are, let's say, very dilute mesh. So then your average electron density in space seems to be very small. And simultaneously, these wires have a very large inductance. So let's say this is your structure, an electromagnetic wave comes in with orientation like that. Let's say this is the polarization vector, vertical. An electromagnetic wave comes in with E field like that, then it will drive currents up and down this wire and these vertical wires, and these will actually, these currents will experience a simply enormous inductance because these wires are very, very thin. There's an electromagnetic effect. Now, when these wires are very thin, that inductance basically is a inertial effect. You can either think of it as inductance, or you can think of it as if these electrons which actually are moving in the wires have become tremendously heavy. So effectively, if you look at the plasma frequency, that electron effective density can become very small, effective mass can be large. So this plasma frequency can actually fall through 4 or 5 orders of magnitude depending on the wire mesh that you provide. So the plasma frequency for a typical metal is in the ultraviolet frequencies. All the way from ultraviolet down to microwaves, you can design these kind of wire media. So this is, for example, how you would do it in the optical. If you have these, there are multiple things, like you can have an aluminum and you can anodize it in an acid to get a nanoporous alumina, and you can fill these nanopores with these are long oriented nanopores, and you can fill them with metal like silver, so you actually can produce a wire-like media at optical frequencies. A denser medium than that would be, for example, if you can grow them in solution under an electric field as shown in this paper and so on. So typically in these cases, the dielectric permittivity is a volume average, fill fraction volume average of the dielectric permittivity of the metal and the background. So depending on how much metal you fill, you can actually make the dielectric permittivity that much negative. So I will go ahead here and explain to you now one effect which is very, very unique to these hyperbolic media. So if you look at these media that I have shown you here, only when I apply the electric field of the electromagnetic radiation is applied so that its polarization is such that the electric field is along the wire, only then it has negative permittivity. If it is perpendicular to these wires, then the permittivity is actually positive. You do something called a Maxwell-Garnett or a Brueggemann homogenization there, but it is overall positive. So what happens is these are media where if the electric field of the radiation is along the wires, you have a negative permittivity. If it is perpendicular to the wires, you have a positive permittivity. So it's a very, very strange situation of anisotropy. And when you have such anisotropic media, it's very interesting to ask for the wave dispersion in these media. When you look at the dispersion equation in an anisotropic medium, this is how you write it. Kx squared by epsilon z, kz squared plus epsilon divided by epsilon x is mu I times omega square c square. So let's say everything is dielectric, mu I is 1. This is for a wave propagating in the zx plane polarized along the y direction. Yeah. No, it's h is along y. Yeah. So it's polarized in the XZ plane. So now what happens is, if you, let's say, one of epsilon x or epsilon z negative, this elliptic equation of an ellipse in the K space changes into an equation for a hyperbolus in the K space. Let's say you make this negative here, you will end up having an equation for a hyperbolus. So now you see that your dispersion equifrequency surfaces of the for the dispersion have all become hyperbola. They are no longer ellipses like what we used to think about. Now that's a very, very, very strange situation. You've never seen anything like that in traditional optics, because we had circles, we had ellipses with a small amount of ellipticity. That's it. We never had this kind of a situation where it was hyperbolic. So what are the main effects then? Suppose you had a wave propagating in the XZ plane from air. This is circle represents the equifrequency surface on air. Let's say the black line is the direction of incidence, and this is the plane. You know, in so you actually come and hit the this plane here. This propagating in the XZ plane, so you hit it on the YZ plane is your interface. Then what happens is the parallel wave vector has to be conserved. That is actually the entire point here. So when you try to conserve the parallel wave vector, suppose you are incident on the XY plane, you are propagating in the XZ plane. This is the parallel component of this region. This is the parallel component of the wave vector, and this has to be equal in the refracted wave and the incident wave. So when you see that, the refracted wave looks that way, and inside the medium. So, but because the surface, the equifrequency surface is like that, and normal to that goes in a completely different direction. So you can actually have negative refraction in such cases. The same thing when the other one is actually negative, and you get a Z hyperbolic medium. So these kind of very strange negative refractions, and not only negative refractions, if you think about an evanescent wave means your K vectors don't fit in on the circle. There is an imaginary part of one of the components, so they're actually outside the circle, but still they can actually couple while keeping the parallel wave vector the same, because you actually have these hyperbolae which go all over space. So that means that evanescent waves can couple into the hyperbolic medium, and they can propagate it in the hyperbolic medium without any issues. Let's look at a physical manifestation, how the permittivities would look. If you just take a stack of positive and negative thin films, let's say of silver and fused silica, let's say SiO2 and silver, alternating layers of 5 nanometers each, you make hundreds of layers. And you ask yourself, what is the effective medium for that? You can homogenize this through various procedures. And if you see that, you can have a band of frequencies where one is negative, the other is positive. Then you can have another band of frequencies where the other is positive, this one is negative, and so on. So you can easily realize such hyperbolic materials with even very simple thin films. Another application is, you see, can I have an anisotropic optical fiber? There's something that we thought of, and it played on our mind, and we found a way to realize this. So you can think about the dielectric permittivity to have a form like this, where you have in the optical fiber, you can think you have the z-axis along the fiber, and then you have the r and theta within the in the the radial and azimuthal coordinates and angular coordinates, and so that permittivity tensor in terms of r phi z can be written like that. And what do I need to do? I need to well solve the Maxwell's equations, that's usual, and then I will assume propagating solutions in the waveguide, and we can use separation of variables, etc. And what we do is we end up seeing that the solutions will consist of Bessel functions, but of imaginary orders. Whenever you have the hyperbolicity where epsilon r is negative and let's say epsilon phi epsilon z as positive, or it could be the other way around also. So for example, what are these Bessel functions with imaginary orders? They are just like normal Bessel functions, but you calculate it similarly, but they are related more to the gamma function. These are actually quite similar to these functions like sine 1 by x, cosine 1 by x. These are things we would have played at the level of 12th standard. If you think of those functions, how they go fine, but when you come close to the origin here, this 1 by x starts becoming larger and larger, so sine of 1 by x starts going through a huge number of oscillations near the origin. So there is an essential singularity at the origin. The same thing manifests here with these functions, Bessel functions with imaginary orders. You have more and more oscillations. Larger the order, actually, the faster the oscillations are near the origin. And that's how they look like, really. These are stranger functions than the normal Bessel functions, but yeah, that's what they look like. So at the origin in these cases, what happens is, if you just see here, if you had an anisotropic medium, what is, you know that the directions are not defined at the origin. And that's the reason you have this singularity of the origin in these cases. But anyway, if you examine how the structure looks like, if you have Bessel modes with real orders, then you get the normal TM or TE modes in the circular waveguide. And what you can notice here is, if you keep increasing the angular order here, you see that increasingly the center becomes bereft of all radiations, and the radiation will get concentrated more and more at the edges. These are what are called the whispering gallery modes in cylindrical or spherical systems. But if you start thinking about fractional orders, by the way, they can also be fractional order modes in these systems. That's the other strange point about it. Then the fractional orders fill out the volume more, but they also pretty much look like the ones with real integral orders, where the Bessel functions are the modes of the waves inside the hyperbolic, in such a hyperbolic medium. But then if you have imaginary orders, this happens when epsilon r is negative, epsilon phi is positive, epsilon z is positive. You will find that the modes start oscillating closer and closer to the center. We actually exclude the center here by putting in a core of some other medium, a dielectric medium or a conductor. We put a perfect conducting boundary condition here so that we understand what's happening. You don't have a divergence, a physical divergence there. And you will find that the modes actually completely populate the fiber. They don't actually go over to the edge here. And there are actually physical implications. When they do that, you can do many things which you can't do otherwise. All right. So the first question is, how do we realize this anisotropy? What we do is to use anodization of aluminum to realize nanoporous alumina. So that's what you do. Usually you take a aluminum sheet and you anodize it. It is covered with an oxide. It gets you anodize it carefully in an acid environment. You get this covered with an oxide. This aluminum oxide is like nanoporous. These pores can be very well oriented if you are careful, if you follow a particular procedure. I can talk about it if somebody has any issues. How do you produce it? But finally, what you have is you have a solid aluminum oxide layer, which is about 30 to 50 nanometers here, and these can be as long as millimeters long actually. See, this nanoporous alumina is probably the nanosystem with the largest transverse diameter to length ratio. Its length is the largest. Then what we do is, we do that in the circular geometry. We take aluminum micro wires, we machine it with electrochemical etching to the right size that we want, and then we do an anodization, and on that wire we then actually create this nanoporous alumina. There's always a core of the wire in the middle, which is not nanoporous alumina, and you can etch out the aluminum by using an acid later. So you can either have air or aluminum. So the core can change. You can also fill it with something if you want. And here you have alumina, so you have pores that go from all the way to outside to the inside, and then there's a solid alumina inside, which actually separates the core from these nanopores. These kind of wires have a lot of other applications also, for which we envisage. For example, these can make beautiful heat exchangers, thermal exchangers, which we have patented. So here are physical examples of what can be done. So you have these nanoporous alumina, you have an aluminum core inside, and you actually can etch away the core to make an air core. And you have these nanopores which extend from outside to inside. The outside looks like this here. And then these pores go all the way from outside to inside. You can see this near the outer surface, they look like that. They are open. In the inner surface, they are closed, and so on. So this is a highly anisotropic system. Now what we do is we electrodeposit silver inside these pores by an electrolysis process, and then we have an anisotropic hyperbolic wire medium, but in the cylindrical geometry. So here we show certain pictures where this kind of a hyperbolic fiber is actually carrying light throughout. This is a bent fiber through which light is going. And here you are seeing, if you couple in light, you actually can displace it to a certain other direction through this bend angle. And this is something that has been imaged. So we have actually seen light going through such fibers. And the issue is we are not able to image the mode structure because there's a large amount of scattering in our present fibers, and we have not been able to fix it. We are not great chemists. We need some good electrochemists to work on this problem. So this is a very interesting nanoporous metamaterial fiber that has been developed. It was developed for the first time in the world. People are quite interested in this kind of systems. And the other thing I would just say is how these become very, very important to couple to the near field of sources. Now, what are near fields and what are far fields? Let's just try to understand that. When you have a source could be a molecule that is emitting, or a nanostructure that is emitting, an antenna that is emitting. There are two principal components. One is a far field component, which is almost like plane waves with small transverse momenta which are going out. They could be spherical waves, but they are almost like plane waves. The wavefront structure is well established. And then you can have near field evanescent modes which are not propagating. Okay. Now these near field components are quite interesting. Because you see, you have these do not actually propagate in sense of a phase front, but these are like modes that are just going up and down in amplitude, in time, and these fields are stuck very close to the surface. Now these can be thought of as plane waves with very large transverse momentum, not momentum in the direction of propagation, but in momentum in the perpendicular direction. And these waves do not couple to an optical microscope because they don't propagate far away from your object. So if you take an optical microscope, let's say to look at some microscopic object, you never see the near fields scattered by that object. You only see the far fields. So what can we do? So we can actually use a fiber optic tip, make it very small to go very close to the object and actually scatter off the near field into a propagating mode into the fiber. That's called scanning near field microscopy. But then this scanning near field microscopy, the mode structures have to match. So, you can have a mode, the fiber mode inside is over a very large area of, several microns. The tip is small, and the tip actually carries a little bit of the near field, scatters it into the mode inside the fiber. So the variation of these near field modes is very fast, perpendicular, along the plane. So what happens is the mode structure is very poorly matched, and the coupling is extremely poor. It's about 10 power minus 8, 10 power minus 9 or so. Of what is the field here, the amount of field you get there is very small inside the fiber. So near field imaging is always, not very easy. Unless your sources are quite bright, you can't really couple it quite well. You can't see them. But so what another thing that you can do is, you cannot take a very small source and let's say you made a single photon source and you have a small nanodiamond which through a nitrogen vacancy emits single photons, but you can't couple it into a fiber easily because the nanodiamond is very small, 20-30 nanometers size. Now your fiber is several microns. So if you just couple it, there's a mode mismatch again, light doesn't go in, it avoids. So what you do is you actually take these nanodiamonds or any other quantum dots and you try to place it close to the surface of a fiber so that it couples in through the whispering gallery modes. So or through a evanescent mode. Coupling efficiencies can be very, very poor. But in our case, because the transverse modes are the modes are in imaginary Besser modes which have very, very large transverse modes, all these near fields will just directly couple in. And that's a big advantage of our system. So for example, if you take our system and look at what you normally couple in, even over several microns distances of length, the power decreases because of reduction, evanescent decay inside the fiber, inside this length, tapered length. But otherwise, it actually completely is still pretty large. So I'll just show you one table here, which actually makes it, let's just focus our attention to this table, which makes it very, very clear what it is. You have a fiber, let's say of length about a wavelength or 2 wavelengths long, and that's a range over which you have to couple it to an optical fiber. So this is just like a small coupler to a normal optical fiber. This axial hyperbolic fiber would couple 10 power minus 10. Our radial hyperbolic fiber would couple 10 power minus 5 of the incident. And the isotropic fiber, which is used, tips that are used now, will couple 10 power minus 30. So you almost have 10 million times or more, 30 million times more efficient coupling in these particular cases. Okay, so this is the big advantage of what this inhomogeneously filled metamaterial fiber can do to do the near field coupling. So these graphs kind of show you also that it couples very nicely. It depends on the position of the source. It responds very nicely to subwavelength displacements of the source. So it is localized very much here, and then the coupling. So you can actually use it for efficient coupling as well as for localization. So you can also use it for scanning such fibers. So this is a completely new idea in near field coupling and scanning that we had developed here. Now we'll shift gears and go to another manifestation of such anisotropic hyperbolic media, where you can grow nanostructures with very, very large aspect ratios. For example, here I'm showing some SEM images of silicon dioxide or calcium fluoride, but they are grown as nanowires. It's like tall grass, where you are having several microns long, but their thickness is hardly something like 20-30 nanometer thick. Or you can have these kind of oriented angular growths also, where you can keep changing the growth. So you have these chevron-like growths. Or you can even make them completely chiral. You can actually have a forest of chiral springs which grow on a given surface. So there are multiple such things that become possible. And how we do it is a very interesting process. We produce it by what is called angular, this large angle depositions, where when you start depositing these are called sculptured thin films, there will be some random nucleation here and there. And once the material starts nucleated, if your vapor flux is coming at a very, very large angle to the normal, I mean, this is, thing. You have the substrates which are or aligned at a very, very large angle compared to the incident flux. So these initial nucleates will cause a large shadow on the substrate. And so no material will ever reach this region. That region will be shadowed out. So most of the materials only deposit on already nucleated centers. So these centers start growing, and taller they grow, the larger the area they shadow out. So after a while, nothing is ever reaching the bottom. These nucleates are growing taller and taller. So you actually get a columnar growth here. And there are, a couple of empirical rules as to what will be the angle of the growth compared to the angle of incidence of the vapor flux. It will typically be lesser, but than the angle of the incident vapor flux, but you can control it tremendously. So this was the system at IIT Kanpur that we had designed. We had built up actually. This is a locally built system to make all these kind of things. Now we pushed this idea much further. We said that if you take a periodically structured surface where, let's say, you have these kind of islands already made, and then you deposit these. If you deposit with a vapor flux at an angle greater than alpha, no flux will ever reach the ridges in between, the valleys in between. All the flux will only fall on the tops here. So all the columnar growth will only from these regions. There will be nothing here. So now you can introduce a periodicity also into the system, a further structuring of a sculptured thin film where you already have the nanocolumnar nature, which I had shown earlier, but you can now further structure it to create more, order in this, and that structuring can be at wavelength scale. So you have a 2-scale structuring here, one at nanoscale, one at 100 nanometer to a micron meter scale, which is what we did. We can take such sculptured, you can structure some patterned substrates. You can pattern the substrates by variety of methods, laser machining, laser interference lithography, or whatever, electron lithography, whatever you want to use, you can actually use. And we typically used the laser interference lithographies to produce these sculptured surfaces of various kinds, square or hexagonal or whatever symmetries we wanted to do by a 2-beam interference and multiple exposures. And we got a lot of things. Now let me discuss one effect that you can do. For example, we created these structures where we take a grating and then we deposit these. So these are deposited on top, they grow out. In this case, they have grown out as if they diverge. These diverge. That depends only on the deposition rate once you have fixed the material and the periodicity. And you can see it's about a micron thick, but the periodicity is around 400 nanometer, about 600 nanometers. So you have a very nice, array of brushes. But then when you look at it, what you see is this system consistently creates triangular air cavities inside this here. Okay. And these triangular air cavities are with very well-defined angles. So what we noticed was when we looked at the diffraction patterns of these were highly anisotropic. I mean, if you take a linear grating with these triangular pyramidal cavities throughout, prismoidal cavities, we find that the diffraction efficiency in one direction is very strong, in another it's very weak, and in the perpendicular direction it's almost the same. And the reason is actually these behave as blazed gratings, right? You have a phase shift as you go across the grating period, and that causes the beam to actually switch in direction. So this is a well-known effect, right? I mean, where you know that if you create a phase shift in the Fourier space, what you get is a angular shift. So this is exactly what happens. So we end up with a blazed grating, and we actually modeled it with some very simple scalar theories, and it could if a scalar theory where we just based on the Kirchhoff-Fresnel boundary conditions, we could understand this whole effect. Now we could also make plasmonic structures like these, where you could actually deposit these almost like nanocolumnar pillars like that, and then they are perfectly very nicely oriented. And now what do you have? You actually have an effective medium of nanopillars, silver negative permittivity with the axis oriented along the pillars, positive in the others. So you have a grating of an anisotropic medium. So we try to understand the dielectric properties of such gratings, and if you can actually do them over nice, if you can model them nicely like this, you see along this axis tau axis you have a negative permittivity, along the NNB axis you don't, and the dielectric permittivity of this effective medium then becomes like this. It is B, C, A, these are the things, and with that when we do our experiments and we retrieve the parameters, we see clearly that epsilon B is negative along the axis and epsilon A and C are positive, and they are around 1.5, 1.6. And so, but the negative one, which looks like plasmonic, also has is associated with a huge absorption as well. But in any case, it has a huge negative indefinite permittivity, and this was something that was a very, very, it's a different way of doing things, and we were very successful in that, and it's a new system that we actually presented to the world. And that had a very, very interesting effect. When you look at the surface plasmons that run on it, of course, you can have all kinds of surface plasmons, but in this system, light, when you put at normal incidence, it will couple only to surface plasmons in one direction. Let me explain this graph, what it is. When you put light on a grating like this, the grating periodicity will let light couple to the surface plasmons running on it if you have a metallic grating. Now, if you look at the transmittance, let's say through a thin metal grating like that, wherever the light couples to the surface plasmon strongly, you will actually get a minimum. And these are the locus of the minimum. And at what it has to be at a particular angle and a particular frequency. So as you change the rotate it and change the angle, the frequency at which it will couple will keep going through. So if you continuously obtain all the spectra at various angles, then you can, and you plot them all together as an angle versus wavelength graph, you will actually be able to trace out the surface plasmon dispersions. But here what happens is, if I have here plotted the surface plasmon dispersions from theoretical understanding, then what happens is you will see that you will have a +1 mode which couples and a -1 mode that should couple in a normal grating. But in such gratings, you will see that only the +1 mode couples, -1 mode is not at all coupling. And it could be for various gratings of various periods. These are different periods and these are different kinds of polarizations and so on. But effectively what we have realized here is a unidirectional surface plasmon coupler. We can couple plasmons to a single direction. And if you make it two-dimensional, it becomes even worse. I think I might have something there. No, I don't have that, but I just say that you can actually get one wavelength of light to propagate as a surface plasmon in a specific direction on the two-dimensional grating. And that's a very important effect because you have directional propagation, which is ensured because you can then channel those surface plasmons very effectively into a surface plasmon waveguide. Now, you can reorient these silver nanocolumns, and we did that by certain, ion beam irradiation. You can actually irradiate these, and then there's a thermal effect that comes about. You heat one side, so there's a plasticity, and the whole thing actually twists towards an ion beam as you keep going. And then because of the heat, you actually you anneal all the defects because of the heat, and then they can get a permanent fixing in direction also. So several times you can make it go up and down. It just depends on the direction of the ion beam. We used a focused ion beam because we had, but you can just use a directional ion beam and you'll be able to get this reorientation of these gratings. So, for example, here is the grating. This is a ion beam image of the grating. It's actually these great nanopillars are lying at a very large angle to the normal. And if you look at the diffraction from that film, you have -1 is very strong compared to +1 order. It's a blazed grating. The moment you actually reorient them and make them look normal to the surface, you get almost the same. -1 +1. Now diffraction orders look the same. Now the transmittance can also be very nicely redone. Now, can we use such gratings and such nanocolumnar systems to extract more light because we couple more effectively to the near field of the system? So will it actually do it? What is the mechanism? Will it do it because it's an anisotropic hyperbolic medium? Or will it be because in the near field, these nanocolumns can act as subwavelength sized antennas? Nice. So the thing is, normally light from an atom or molecule does not couple out very effectively because of the classical electromagnetic effect that these are very small compared to the wavelength of light. They basically act as subwavelength sized antennas. So subwavelength sized antennas are very poor emitters. So what we thought we could do was nanodiamonds, which NV are very interesting quantum sources of light. That's because the source is embedded in a nice protective environment afforded by the nanodiamond. The question was, can we extract more light from such sources by coupling them to hyperbolic thin films? This is what we actually started doing. So what we did was we made such films, we spin coated them with nanodiamonds, and these nanodiamonds are sitting on top of these rods, as you can see, and these nanodiamonds, there's an AFM image and so on. So they have these very nice emissivity of these nanodiamonds, and this is what is called the Bullrand, the peak emission, which is broadened by temperature in this case because these are done at room temperature, these experiments. So what we did was to use confocal microscopy to start looking at these diffraction limited spots. We assumed that they would be single nanodiamonds. Typically they are. And when you place over these nanodiamonds over the silver CTF, many of the nanodiamonds actually started emitting a lot more. And if the columnar thin films were on a grating, some spots became extremely bright. But there was a big distribution of emissions. So what we did was, we said, let us actually look at this entire statistics, distribution of emissions from several samples. And this is what is the end results of almost something like 100 odd experiments. So if you just take them on glass, you get occurrence of very bright intensity is very less. This is the brightness scale on the x-axis, the occurrence of those bright spots on the y-axis. So if you just put them on a rough silver film, when I say rough, it's about 10 nanometer few nanometer kind of surface roughness, not even 10, few nanometers, and you will find that you actually get decent number of spots per second, decent number of intensity. And when you make it a silver grating, it is typically similar. But the moment you bring in the silver, columnar thin film, then counts where you get very large emissivities. The axes are all the same in all the cases of the figures, becomes very large. And the same thing when you do it with the silver CTF on gratings of various periods, you can actually get very large spots with very large emissions. We just used to take samples and look at the brightest spots in them and try to look at them and then do some statistics, at least for the brightness side of it. We never observed anything like that in these kind of other normal samples. So what we understood was, we did try to do the lifetimes and so on. Lifetime measurements were not very encouraging. That means in each of the nanodiamonds we had a distribution of lifetimes. That means they were not single photon source. But what we can nevertheless say that there is a huge enhancement of the emissivity, and that happens principally because of the orientation of the silver nanorod. This nanodiamond is sitting, and the dipole on it excites a huge current on this silver nanorod. Now that nanorod is a large dipole antenna, and that can radiate much more effectively, and our simulations etc. showed that the radiation can be quite angular, there are symmetries of the angles and so on and so forth, depending on the axis of the nanocolumns. So I think I have shown you 2-3 applications of these hyperbolic nanomaterials, metamaterials, and there are some of the acknowledgements to my collaborators and past PhD students at IIT Kanpur who did all this work. So I think we can have a longish discussion. There's a lot of time. I would just like to stop here. I don't want to pump you with too much of concepts in a short session. Thank you.
Thank you, sir. Thank you very much for such a nice talk. So the questions, if anyone have any kind of doubts, please.
Hello, sir.
Hello.
Good afternoon, sir. Sir, my question is on terahertz metamaterials. So, I want to ask, what is the future of terahertz research in India with respect to terahertz source generations, detections, and the metamaterials, terahertz metamaterials research?
Okay. Good question. Terahertz. The future of terahertz radiation is immense. We need people to work on applications involving terahertz, because you can use terahertz to do security applications. You can, for example, screening at an airport without being intrusive. You're just watching people. Or you can look for mines on a minefield. You can use terahertz for that. Or you can do many more interesting things like detections, sensors for trace materials like drugs or explosives and so on. So there is a variety of security applications there. The other thing that we should be very good at is, can we actually take terahertz spectroscopy somewhere, further, which is also something that has not been done a lot in India. You can use it for, structural health monitoring and so on for certain kinds of materials, metals, and so on, which can be quite deep compared to infrared structural health monitoring. But the critical thing in terahertz is you don't have easy sources of them. You have either quantum cascade lasers, which are quite expensive, or you have these femtosecond laser sources. You actually take a femtosecond laser pulses, put them onto a photoconductor, and generate an immense pulse of electricity for a very brief time. And you look at the Fourier transform of the time for which you can do it, you will get terahertz band. So you get a short pulse, current pulse, which you are actually exploiting to generate terahertz. So you get pulsed terahertz there. So these are the two principal methods of developing terahertz. But unfortunately, if you just ask for a femtosecond laser, today you're already talking of the order of at least, even a fiber femtosecond laser of low intensity, you're already talking of about 50 lakh rupees. So terahertz sources have been extremely expensive. And that has actually prevented work on terahertz across the country. There are a few labs, TIFR, Bombay, Hyderabad, University of Hyderabad, and I think IRD, DRDO has done something. DEAL, I think, has done something in Dehradun. And there are a few more, ISRO is trying something and so on. But you see, the point is, it has been, the terahertz research has been confined to very, very highly funded laboratories only. It is not ubiquitously available. So what is the future of that? I think in the present scenario, unless you can tie it up with a very specific application, you're not going to get any funding for terahertz research. Government, I don't think, is inclined to give you open-handedly, go ahead, buy a terahertz source and play around with it. I don't think that's going to happen. So you need to be very focused on applications and drive your research to applications, then you can do it. Now terahertz, handling terahertz, how do you handle terahertz? You will probably be using mainly reflective optics, or you may be using a few refractive optics, but you don't have too many materials to do it without absorption, or have enough refractive index and so on. So their metamaterials, structured dielectric materials, dielectric metamaterials or metamaterials can give you a huge leeway in handling terahertz. So it would be very useful to develop metamaterials. But the problem with terahertz has been the sources and the detectors. It's expensive. It's an expensive business trying to do terahertz.
Thank you, sir. Thank you very much. Any other question? So if anyone have any other question, even if later on, just write to us and we will forward the question to sir. And I hope he will even later on he will answer this. So thank you very much for nice talk and nice information in this particular field. And as we all know, you are the master of this particular field. So the information you have given in a so lucid manner, so I think everyone, most of us can understand this subject.
Yeah, either people didn't understand anything or they understood everything if there were questions, So yeah, I'm hoping it is the latter. But if you have any doubts, you can always write to us.
Yeah, thank you, sir. Thank you.
Thank you so much. Yeah? Namaskar.
So, Upin?
Yes, sir.
Now, so we may take the break.
Yes, sir. Actually, the time is for break. So the this session will be scheduled at 3 p.m., sir, or?
Yeah, 3 p.m. Yes.
Okay. So all the participants are requested to leave this meeting and they can rejoin at 3 p.m.
3 p.m. Yes, please.
Okay.